Good morning and welcome back. Today this is the final lecture for E210. So we were discussing about BJTs in the last class, and just like we introduced PMOSs, we don't want to look at BJT from the circuit designer's perspective as a different device. You treat it as more or less a similar device like a MOSFET, in the sense that at least eyeballing the characteristics, they look similar. Obviously, the details are different in the sense that the input, the transconductant characteristics, right? That is the IC versus VB characteristics in case of a MOSFET was square law. In case of a BJT, this is exponential, right? So that is one detail that is different. Another important detail that is different is in a MOSFET, your input current, the gate current was 0, but in this case, your gate current is proportional to the collector current. But otherwise, if you just eyeball the characteristics of at least the input-output characteristics of these two devices, they look similar. So which essentially means that the small signal models should also look similar, which means that all the analysis that we have learned throughout the course all apply. The only critical difference is in case of a BJT, there is an input current, which means your Y11, which we considered to be 0 in case of a MOSFET, is not 0 in this case. And some other important details that are different are the fact that in case of a BJT, in case of a MOSFET, the edge of that saturation region, right, the good region, the edge of the good region was dependent on the value of the drain voltage. In this case, or rather the difference between the drain and the gate voltage, in case of a BJT, it's not. So one of the reasons it's not, the intuition behind that is I was not in charge. So essentially, it depends from where you start off, right? So in the sense that if you start off from the characteristics on the left, then you then you essentially, in case of a MOSFET also, if you saw, if we increase the VGS, it kept on increasing the VGS beyond certain VGS, it would have been hit by the linear region problem, right? So essentially, one could say that in case of a MOSFET, it was going like this, then it was going like this, correct? So one of the reasons this goes in a straight line was because one can say that the dependence of the current on the input gets saturated, right? So this was going like parabola, then the dependence became less significant, right? So that is one. I mean, similar things happen in case of a BJT. I would guess that is why they named it. But I mean, so since BJTs, I mean, the history of MOSFET and BJTs are kind of intertwined. MOSFETs came before BJT, then it got dumped. Then BJT came into picture. Shockley promoted BJT, and BJT was there for about 40, 50 years. Then all the terminologies went in BJT's way. Then when MOSFET came into picture again, when IC design industry took fancy to MOSFETs, so essentially said that, okay, similar to this, what can we do? MOSFET has a velocity saturation, all those things will come into picture. So we just say that this is what it is. Whatever we can match, we'll match. Rest, we'll say it's different and live with it. So sometimes that's why in MOSFET, because of this confusion, people normally don't call this. I mean, now they call, but initially some of them said that we'll not call this region saturation region, we'll call it pinch-off region, because there was a pinch-off phenomenon. So that saturation region terminology stuck with only the BJTs, and in case of MOSFETs, we used to call it linear region or pinch-off region. But then something else happened, that we saw that, I mean, we didn't talk about this, but there is another phenomena called velocity saturation that happens in MOSFETs. So if you reduce the channel length sufficiently small, then the pinch-off doesn't happen, but the maximum velocity with which a carrier can go gets saturated. So that happens in this region. Then again, people started calling it saturation region. So essentially the naming is checkered. So I'll not get into the, I mean, why, who gets to name what. No, that is more than technical. Beta is a constant. I mean, ideally it's a constant, but again, nothing is ideal. But yeah, for all practical purposes, beta is constant. Okay, so a very crude structure of a BJT, without going into the details of how it is made is the following. So if you take two diodes and connect them like this and control this terminal, this diode have to be made in a certain way. It's not like you can slap together any two diodes and it will work. Then you can say this is, if I call this C, this is E, this is B. This, crudely, these two diagrams are equivalent. Very crudely, these two diagrams are equivalent. So if you just look at the structure, the way the BJT is supposed to work is the control terminals are VBE, which means you have to have, generally in order to get an amplification, you have to apply an input between VBE. And when you are trying to get a collector to swing, that is, you want a gain between collector and emitter, you are taking these two. You are essentially observing the voltages between these two terminals. Okay. So in other words, this sets the current to some extent, and there is certain current amplification that happens that is equivalent to the GM term in case of a MOSFET. Okay. So now for this to work, this let me call this diode the collector diode, DC and DE. This DE has to be forward biased and DC has to be reverse biased. That's how the BJT works. So in order to keep this VCB, in order to keep the VBE diode or the DE diode to be forward biased, you need approximately, not only forward biased, you need this diode to be on. So typically the cutting voltage of diode that we associate with is what, 0.65 volt, 0.7 volt or something. Again, we know that is an approximation. For certain current range, we call that a cutting voltage, but if the current range changes, that voltage can also change. But just like we did in case of a diode at the very beginning of the course, you can say that this voltage is at 0.65 volt. If the diode is on and operational. Similarly, because the collector based diode, that has to be reverse biased, so this has to be at least 0 volts in the other, right? If collector goes below base, let me write it in this form. If the collector goes below base, then DC tends to get forward biased, right? So that's when the BJT action gets lost. So that's where when that starts to happen, you kind of enter this region. So in other words, you would want at least how much drop between collector and emitter? Between collector and base, you want at least 0. And between base and emitter, you want 0.65. So between collector and emitter, you would want 0 plus 0.65, that is 0.65. Okay. So that's why in case of most circuit designers, so I made one mistake in the previous, in the last class in marking where this 0.65 node is. As it turns out, this 0.65 is not here. This is a bit away from this junction. And the reason it is slightly away from the junction is because we know that even though ideally, in order to forward bias a diode, you can give any positive voltage, like if you give 0.1, 0.2, doesn't really matter. Ultimately, we know diode is exponential, so e to the power 0.1 by et is also quite high. However, in order to achieve certain amount of current, right, in order to truly get a diode to be operational with certain voltage, with certain amount of forward bias, this 0.1, 0.2 are typically not sufficient for the typical currents we use. So generally, those ranges of currents you will get if you at least get to 0.3, 0.4 volts of forward bias. So essentially, this knee is about 0.3, 0.4 volts away from 0.65. So that's why this is approximately 0.2 volts. But that is a matter of detail. We will not get into that. For us, for circuit designers, all we have to ensure is that we don't get into that murky zone of whether it is actually forward bias or not. So we'll have to make it fully reverse bias. We'll get here. We'll operate here. Okay. So in other words, we'll have to ensure that. So in other words, we have to ensure that GCB min has to be 0. Okay. So this will be important for your swing limit calculations, right? How low can a collector go? How low can a collector voltage go in order to, while keeping your BJT in proper operating conditions? Again, just like in diode, a forward bias diode, while calculating quiescent conditions, we assume the drop across it is 0.65, regardless of whatever happens. Similarly, because a BJT is a back-to-back diode, we can also say that DBE is equal to 0.65 volts. This is for quiescent calculations. Okay. Now, there is another set of terminologies that I'm sure you were familiar with from your ESC 201. So since this is a back-to-back diode, and these are PN junction diodes. So let's say I concentrate on this diode. Then this terminal, in terms of doping, this terminal is P, this terminal is N. Right? The PN junction diode, one terminal is P, the higher terminal is P, other terminal is N. Similarly, in case of the top diode, this terminal is N and this terminal is P. And since they are sharing those two terminals, two P terminals, you can remove one of the P. So this is called an NPN BJT. So just like you have an NPN BJT, you also have the complementary of it, that is a PNP BJT. That is the equivalent of whatever, just like if you have a PMOS, which is a complement to NMOS. Similarly, you have a PNP, which is complement to NPN. Again, equations are same, polarity is reversed, small signal model, exactly the same. Okay. Okay, fine. Questions? Okay. Yeah. So just like you have a MOSFET, a source. In case of a in case of a P MOSFET, you have a current flows from source to drain, and this is the gate. So in case of a PNP, this becomes the emitter, this becomes the collector, this becomes the base. Okay. Now the question comes as to how do we bias this transistors, right? So we can take the examples of whatever you did with MOSFETs, we can do the same things in case of BJTs. So in case of a MOSFET common source amplifier, we started off by doing this, right? So in case of a BJT, we can also plan to do this. So let's not put this RD just for the biasing, we don't need the RD. We can simply connect it to a higher supply. So in case of a BJT, in case of a MOSFET, we figured out this voltage. We figured out this voltage, the gate to source voltage based on the requirement of the current of M1, right? So this current is proportional to W by L VGS minus VTN whole square. However, note that this current, in case of a BJT, is IS exponential BBE over VT. One key difference between the MOSFET and the BJT is that BJT doesn't depend, the current in the BJT doesn't depend on its size. right? So in case of a MOSFET, you can change the current by changing its size, right? It's not as if you make a bigger BJT, you get double the current. In order to get double the current, you have to put two BJTs together. Okay, that's how the nature of the structure is. Another important thing is that because the side effect of this is the GM of your MOSFET is, if you bias it with constant current, or even if you don't bias it with constant current, is, let's say you bias it with constant current, the expression is mu. But what is the expression of GM in case of a BJT? GM of a BJT is what? You know the current, you know the input variable. So del I, del VBE, which is basically its exponential, right? So del IC, del VBE. So this becomes IC over VT. Right? So the critical difference is that the GM of a BJT is independent of its size. In a MOSFET, you can keep on increasing W for certain current. You can get higher and higher GM. But in case of a BJT, there is no option. You just have to increase current. Okay, so you don't have that luxury. So this is probably a luxury that a circuit designer wants. However, if you are designing discrete circuits, right? If you are designing discrete circuits, that is, you have a breadboard and you are putting transistors together, then you don't want cases where if you need higher GM, so you have to put 2 transistors together or 4 transistors together. Simply the board becomes very clunky, right? Wiring becomes difficult. But in case of a BJT, that's not the problem. It's a pretty strong dependence on current. The GM of the BJT has a linear dependence on current, whereas GM of a MOSFET has an under root dependence on current, right? So essentially, it's easier to change the GM of a BJT than a MOSFET if you are constrained for number of components. You can just simply change the current and GM goes linearly. So that is why one of the, even in today, the discrete circuits are made using BJTs. Okay, simply because it's easy to make, it's easy to change, it's easy to get a wide range of GMs using BJT, and it's more convenient. No, you use MOS for both digital and thing, but I'm distinguishing between IC design and discrete level design. When you are doing on boards, like you are varying breadboards, so then the size of the component matters, right? So you don't want to put 10 components just because you want 10 times of GM, right? So board size also matters, so it becomes difficult. But in case of a BJT, it's pretty simple. So you simply increase the current, 10 times it will increase. In case of a MOS, if you increase the current 10 times, your GM will increase 3 times. Approximately, right? So that's a trade-off. Okay. Now another critical difference between MOS and a BJT is this. So if you bias your MOSFET like this, your GM we saw is dependent on temperature and so on and so forth. So this is probably not a very good way of biasing. Not probably, this is not a very good way of biasing, but still it will work in the sense that your GM will vary a bit, but it will work. But as it turns out, if you hook up your BJTs like this, it will never work. The reason is there is a certain aspect of BJT which deals with temperature dependence. By that, what I mean is the IC VBE plot for a BJT is supposed to be exponential. That's true. However, as it turns out, if you increase the temperature of the device, the current increases. That's how the nature of the device is. So which essentially means that if you increase the temperature, this plot shifts to the left. Right? For the same VBE, you get higher current. Right? So this is the increases. Now, why is this important? This is important because when you turn on your circuit, it draws some current. When it draws current, it dissipates power. When it dissipates power, it heats up. When it heats up, if you are biasing your BJT like this, it heats up, the current increases further. it hits more, current increases further, and it keeps on going till the time the device burns out. So this effect is called thermal runaway. You don't need to remember that this name of the effect, but what you need to remember is that if you bias your BJTs like this, it will burn out. So what is the solution? The issue is the current is not limited. The current keeps on increasing, right? Because you have biased it with constant VBE, and since you have biased it with constant VBE, you have no control on whether the current on through the device is limited or not. Okay. So what is the solution? Well, primarily that will not help, because the current is not primarily dependent on whatever is connected on the collector, right? Just like in a MOSFET, if you connect a resistor to the drain, it doesn't really affect the current, right? It will go out of your region of correct. Yeah, so that you don't want, right? So okay, I mean, okay, it will not probably burn off, but I mean, you'd also want to make an amplifier, right? So you don't want to do that. So among all the biasing techniques that we have learned, which one you think is more appropriate to bias a BJT? Principles are still the same. So you have to limit the current, essentially, right? You have to limit the current and ensure that even if temperature increases or whatever happens, the current through the BJT doesn't change. So what do you think? Current source biasing, right? You limit the current, right? You just put a current source. So essentially, what you can do is you take a BJT, put a current source, and then you can apply whatever you want here, right? Yes. Okay. So as it turns out, BJT has a property that it has a negative temperature coefficient. By that, what I mean is there is if temperature increases, the current increases. So that's how the device is. Okay. So you see there is an electrothermal positive feedback here, because you turn on the device, there's some current flow. When you have some current flow, there's some power dissipation. When you have power dissipation, it heats up. When it heats up, current increases, right? Current increases, and then you have more power dissipation. It heats up more and keeps on going, right? So it's a positive feedback. However, in case of a MOSFET, it's the other way around. It's an electrothermal negative feedback. It has a negative temperature dependence. It has a negative temperature dependence, which essentially means that if power increases, current decreases. So it quickly balances out in a. So there is essentially it's an electrothermal negative feedback loop in a BJT in a MOSFET, but it's positive feedback loop in case of a BJT. I mean, having said all of this, the solution is pretty simple: bias it with a constant current source. So now, if you bias it with a constant current source, let's say this is VDD. This is 2 volt. This is VDD is equal to 5 volt. This is 3 volt. This is 2 volt. How do you think will you approach this problem? But let's get into biasing first. So what is this voltage? 2 volts. So what will be this voltage? 2 minus 0.65, right? 2 minus 1 VB, and VB is always 0.65. So this is 0.65. So this is 1.35. And this is 5 volt. Then you are good. So then if you want to make, if you want to connect a load here, you put some RC, right? So the value of the RC will depend on what? Now, while you want to keep this device in proper working condition, the active region in this case, it will depend on how much current source you have here and what is the drop across RC. And how much can this drop? Yeah, how much can VC drop before the device goes out of your region of operation? We are trying to keep it in active region. Right. Yeah. So again, yeah, correct. 0.65 is always fixed, but you don't have to even know that, right? All you need to know is that just in case of a MOSFET, the drain could have gotten one threshold voltage below. In this case, the collector can go as slow as a base. That's all, right? So if this is 2, this can go at minimum, VC min will be 2. Right? So as far as your swing limits calculations is concerned, this is the only difference. Right? So we do same small signal plus incremental, but the limits are this. So similarly, so now you will see that in most BJT circuits, sometimes you cannot afford to have a separate current sources. So a port one's current source is a large resistor. So this is quite often used. So let's say this is 2 volt. This becomes 1.35. If this RL is, let's say 1K, then this, this current will be 1.35 milliamps. Okay. So that's why finding quiescent in BJT is pretty straightforward. You can just simply look and write. You don't even have to do any calculations. Okay. Any questions? Pardon? Yeah. Yeah. So this is something that you will do in your labs also, in 380 labs, right? So just, I mean, you can, especially in boards, you cannot have, it's not very trivial to get current sources. So a replacement of a current source is essentially a large resistor, or whatever is large is dependent on the context of whatever is connected to, right? So in this case, the large will, from whatever we know using MOSFETs, what value of RL do you think is large enough? So RL has to be infinity, ideally, but infinity is not possible. So given that I have to deal with some level of RL, what do you think is what is the constraint on RL that determines whether RL is large enough? Assume this is a MOSFET, then what constraint on RL do you think we have to impose to understand whether RL is large enough for the current to be determined by in this fashion? So remember source follower architecture. GMRL much greater than 1. In other words, the voltage, the impedance looking up has to be much less than impedance looking down. Right? So similarly, in case of a BJT, it will be that, right? Whatever impedance looking up has to be compared with the impedance looking down. So that brings us to what is this impedances looking on different sides. Yes. In this case, yes, right? Correct. What you are saying is absolutely correct. From the context of whatever you are saying, that if RL goes to infinity, current will be 0. Absolutely correct. But from the context of the impedance of a current source, right? The impedance of a current source has to be infinity. So that comment was based on that context. Okay, fine. So in case of a BJT, now what is a small signal model of a BJT that we did yesterday? So in case of a BJT, okay, so let me okay, when I'm drawing the small signal model, I'll make that comment. So a small signal model of a BJT in case of is the following. So this is GM BBE, this is R pi, this is some RCE. Now there was one comment at the end of the last class was our base current is not 0 and base current was IC over beta, where IC is whatever IS e to the power VB by KT by BT by beta times 1 plus VCE by VA. Okay, so it seems like there is there is a dependence of IB on VCE. Correct? And there is, in fact. So which means that there should be a Y21. Sorry, Y12. There should be a Y12. And in fact, there is. Your Y12 is del IB del VCE, which is approximately IC by beta VA. Right? So if you just massage the equation, this is what comes out. But having said that, this Y12 value is pretty small because beta is quite high, VA is quite high. So this Y12 value is quite high. So that's why in most cases we tend to neglect it because it's an unnecessary complication that doesn't add too much of a value. Okay, fine. So now, in case of a MOSFET, if you had applied a test voltage, assume that this is bias in saturation and all, right? So in case of a MOSFET, so the equivalent of this circuit was you apply an RL here, and RL incrementally goes to ground. And in case of a MOSFET, if I try to figure out what is the impedance looking in case of a MOSFET, this Rin was infinity because you are looking into the gate, correct? But in case of a BJT, it's not infinity because there is an R pi connected. Okay. So what is the effect of this? You can find out. You apply a V test, you have a current I test. So this I test flows through this R pi and it creates a voltage of I test times R pi. So your VB now becomes I test times R pi. So this current is GM times I test times R pi. I forget about RCE for the time being because that will, that doesn't have significant effect because current division will not happen through RCE because that is supposed to be quite high, right? I mean, just in case of a MOSFET, we wanted the TDS to be quite low or RDS to be quite high, you can make the same approximation. So this current that comes through RL is summation of these two branches. So essentially this becomes I test plus GM R pi I test. So this voltage becomes this times RL, right? So if I write the KVL in this loop, so this becomes V test is equal to I test R pi plus so your V test over R I test, that is Rin, becomes R pi plus RL plus GM R pi RL. So this is a side effect of this. This is not infinite. This is not infinite because you have a finite base current. Okay. And this expression is again pretty similar to the output impedance expression that we found in case of a MOSFET, where you had something connected to the source and you were looking in from the drain, right? Cascode cases, right? So summation of two individual resistances, which we expect, plus the resistance that is connected to the emitter gained up by the intrinsic gain of the MOSFET, right? In this, gained up by the intrinsic gain of the transistor. So since when you are using BJT, it is expected that the BJTs have a pretty decent gain. So in this case, this GM R pi can be much greater than 1. So this often dominates. So this can be GM times R pi times RL. Okay. So similarly, you can do the small signal analysis of looking in from the emitter. So what happens? So I'll send out an assignment sheet. You can hone your skills on that. Okay. Any questions? Okay. So now, so essentially everything that we have done with MOSFET, all circuits possible with BJTs. So I'm only pointing out the critical differences that you need to take care. One critical difference that comes along with this, one critical difference that appears because of this base current is the effect on current meters. So in case of a MOSFET, you had this structure, you have something connected here. But in case of a BJT, if you also connect it like that, the problem is now you have a base current. So in case of a MOSFET, we had connected drain to gate, right? Just like that, because one of the reasons was we wanted to get this magic voltage, right? And so that we can copy that voltage n number of times if we require. But that was possible because wherever we connected, it was not drawing current, right? Had it loaded, then this voltage would have dropped. So it wouldn't have been the magic voltage that we want. So that's what will happen in case of a BJT, because each BJT you connect will load this diode connected configuration. Okay, so if this is I0, and let's call this IC. So this current will be IC over beta. This current will be IC over beta. So this current will be 2IC over beta. Correct? Yeah, so we'll see. So the right current will also be IC. Correct? That I agree. Right current will also, right hand side current will also be IC, but I want the right hand side current to be I0 because I'm mirroring I0, right? So, but what is IC now? So if I do the KCL at this node, right? So what is IC? So IC plus 2IC by beta will be equal to I0. Correct? So IC is I0 by 1 plus 2 by beta, which is approximately 1 minus 2 by beta. Right? So you have, so you see that the amount of current that is getting mirrored is not I0. This is I0 1 minus 2 by beta. And if you have n of them, right, then it will be I minus n by beta. So your current mirroring efficiency goes down because of the loading effect. Okay, so the difference between the MOSFET and the BJT is the fact that when you connect, in case of a MOSFET, this current is 0. Correct? So in case of a BJT, when you connect it in a similar configuration, this current is non-zero. Right? So the effect of this non-zero current is that you are not generating the voltage across the VBE of the BJT that you want in order to get I0 current. You are generating a voltage in order to get a reduced current, because now there is a current division at this node. There is a current division at this node. So the current that is going into the collector is lesser than I0, and that will get eventually mirrored. Okay, because again, VB is same between both, right? Just like in case of a MOSFET, you have VGS same. We'll have, if I neglect channel length modulation effects, right? Those type of effects, then both will be VC. I see. Yes. Okay. Yeah. Carry out your question. Yeah. Yeah. So your question basically boils down to the fact that what is a BJT? Is it a voltage controlled current source or a current controlled current source? Right? Because I am saying that IC is equal to beta times IB, right? Then it seems like IC is dependent on input current. So it seems like it's a current controlled current source. But alternatively, my equation is also IC equal to IAC power exponential, exponential VBE by KT. So then from there, it seems like it's a voltage controlled current source. As it turns out, it's both. You can model it in either way. But whatever you fix, it will respond to that. If you fix IB, it will respond to IB times beta. If you fix VBE, then it will respond to e to the power VBE by KT, by VT. So the side effect of that is if you fix IB, then VBE will change accordingly. If you fix VBE, then IB will change accordingly. So it depends upon how you set up the circuit, whether it will behave like a voltage control current source or a current control current source. Okay, good question. But since we have learned everything in terms of VCCS, we will also follow VCCS. And that is all. That is one of the best practices, because ultimately we want to limit current. We want to apply some voltage at the input, so on and so forth, right? So it makes sense to treat it as a voltage control current source. But having said that, if you look into the literature, you will find that it has been treated as a current control current source also. Okay. So the problem, this is a problem, whatever I have shown here. The problem is, because of this problem, what is the solution? The solution is basically you have to put a voltage buffer between these two nodes. You have to put a voltage buffer between these two nodes so that you don't draw current, right? Input impedance should be high, output impedance should be low, and so on. And simplest voltage buffer that we knew in case of a MOSFET was what? The common drain source follower, whatever, right? So the same structure holds in this case. So that's why in case of a BJT, the current meters are done in this way in most cases. Okay. So ultimately, we don't want any loading between these two nodes. We don't want any loading between these two nodes, but we want those two nodes to follow each other, right? So that's essentially we want a buffer. So the buffer, in case of just like in case of a MOSFET, in case of a BJT, you put a source follower. And note that in case of a MOSFET, you had to, if you had done something like this anywhere, you had to put some current source here in order to provide the biasing current. But in this case, we are using this extra transistor because there is already a current, and we want to ensure that the current is not loading the previous stage. So essentially, you don't have to put anything. This will auto bias. Okay. So, and how will it do? How will it auto bias? If this is I0, let's say this is IC. This current is still IC over beta. This current is still IC over beta. So this current is IC over 2IC over beta. Correct? So this current will be 2IC over beta squared. Right? So the current IC, the KCL at this node becomes IC plus 2IC over beta square becomes I0, which means IC is which is approximately. So this is much better than this, right? Exactly, right? So that's why when you see BJTs, you will see that current mirrors are seldom like the way we not always, but in some cases we still have current mirrors with direct connected configurations. But in critical cases, you will see that current mirrors are done in this manner. Okay. In this case, it's not necessary because the bias current is being provided by the two leakage paths, essentially. You mean in a BJT circuit, you want a MOSFET? Yes, you can. So there are some BiCMOS technologies where you can configure both MOSFETs and BJTs. By the way, that is not a very common technology. So as it turns out, you can in most technologies you can either have a MOSFET or a BJT, but there are super expensive, but there are technologies where you can do both. There you can do all sorts of stuff. Okay, fine. So another, I mean, so essentially, when I send out a practice problem set, you will see that most of these will be there. But I mean, in the last 5-6 minutes, I would like to show you something which obviously will not appear in the NSEM, but I think it should be it will be necessary in order to have a proper culmination to the course. So so if we if we do the differential pair equivalent of this, right? Of whatever we did in case of a MOSFET, the differential equivalent of pair equivalent of that is this. So you have a second stage, and the second stage has a PNP, and you have a compensation capacitor, right? But one quirk about a BJT is its PNPs are not as good as NPNs in terms that their current gain beta is pretty low in case of PNP. So wherever you want to get a gain, that's why people tend to say that we'll not use PNP, we'll use NPN wherever it's possible. Okay, so this is PNP. So if we have to use an NPN, right? If we have to use an NPN, what should we do? We should say that we want to do this. Correct? But as we talked about in the last class, this has a problem of biasing this voltage. This voltage, when you put in feedback and go down and so, that becomes a problem. But this problem can be fixed by making the input stage PNP. Right? If I make this input stage PNP, so that problem, so basically complementary to whatever we were doing. We made the output stage from PNP to NPN, so we made the input stage. Sorry, it goes from here. So we made the input stage PNP, but one will argue that the same problem, right? Now the input stage is PNP, you will not get enough beta. So what people came up with was this idea that we'll have to use NPN in both cases, right? Yeah, that is not negotiable. We'll have to use NPN in both cases, but we want to ensure that the biasings are fine. So what if we do this? We get rid of the current source from top, and let's say it is connected to VDD, and we use NPN. But now looking into the emitter, you cannot connect it here because looking into the emitter, your gain is pretty low. Your impedance is quite low. So what we do, we put a current buffer. So the current buffer equivalent is this in case of a BJT, and we observe this node. So now all the current can go in. The impedance here is high because you're looking into the collector, right? So this is a PNP. This is NPN. This is PNP. So this is collector. The collector impedance is high, and you can put whatever. You can put a current mirror here again of a NPN. Something like this. And instead of a current mirror, you can use the equivalent of that, and you take it and connect it here. So the reason I'm showing you this is because this is what is done in a 741 op-amp. Don't worry, this is not coming in the MC. But I mean, if you see a structure, now you should be able to deconstruct it. So now, see, these two are the input pair, right? These two are the input pair. This is the current buffer. This is the current mirror that we talked about. This is the first stage output. Now, since 741 op-amp can operate over a wide range of supply voltages, so you have to ensure that the biasing is proper. So what generally is done, this first stage output is not directly fed to the second stage. It goes to a level shifter. By level shifter, I mean Q17 is supposed to be the second stage. So as it turns out, there are some issues if you directly feed this to Q17. So essentially, you need to buffer it again. You need to buffer because ultimately Q17 will draw some current in. You need a voltage controlled voltage source in order to ensure that Q17 doesn't load basically the second stage doesn't load the first stage twice and twice. So you need another buffering stage. So that buffering stage is done by this Q15. So this is this common collector or source follower, emitter follower configuration. So this increases, and similarly, so this becomes your output, right? So this you assume that this is shorted. That is done for level shifting purposes, just to have a difference in voltages between these two nodes. That you can assume it to be shorted. So the second stage, so your Q17 gives you the second stage. This is the second stage incremental current. Q13 gives you the active load. So you have a voltage swing here, you have a voltage swing here, and this output structure you have done in one assignment in terms of MOSFETs. You had a NMOS on top, PMOS on bottom. So this is what it is, because the output impedance looking in is of the order of 1/GM, right? So that essentially is your 741 op amp. These everything else that you see are essentially done for biasing purposes. Yes. Q4 was the current buffer. So note that these are not PNPs, these are NPNs. Right. So the incremental current that would have generated, you would want, so if you had connected it directly here, right? If you had connected directly here, the impedance at this node is high. So it would have been a source follower almost, or emitter follower architecture. So you wouldn't have gotten the incremental current. You get an incremental current in case of a MOSFET if the looking down impedance is 0 or low. Right. So in this case, looking into the source is low or emitter is low. So the PNP gives you that flexibility. So you put a PNP there. It's essentially a current buffer, similar to that of a MOSFET. So that's how you go about doing it. Okay. Okay. So that is as far as 741 is concerned. And in case you want to pursue a career in circuit design, I wanted to just take 1 minute to show you what is stuff that you do. So this is one of the works that we did. This is a filter. Don't have to go into details of that. So this is essentially op amps, single stage op amps connected one after another. If you essentially make a chip and fabricate it out, so this is what the chip looks like, the one on the top. So this structure, this ladder structure that you see here are basically op amps connected here. Obviously, it's not visible. This is the top level. If you put it under a microscope, this is what you get. When the boards that you get, right? Normally, when you design PCBs in order to test your chips. So in this particular case, this is the chip. So this is this stuff, and everything else is essentially to give power supplies and so on. So this kind of gives you an idea of why IC design is important, in the sense that this stuff here probably has thousands of transistors, but see the amount of area that it takes on the board, right? So yeah. So I'm sure I'll not see all of you together in another class again, where I am co-instructing or instructing. So just wanted to take the opportunity to show you this. Okay, thank you. Thanks a lot that we come to the end of this. I had fun. Hopefully you guys remember something, right? Even after the end. Thank you.